Yeah, hello guys. Am I audible? Could you type chat or something? Yeah, okay, good. Nice. So I am Arya Krishnamurthy, and today I'll be trying to do my best to discuss with you all about some games, and I think you will enjoy the session. So yeah, so today we'll be discussing very specific types of games, and they're called combinatorial games. So basically, a combinatorial game is a two-player game that satisfies the following conditions. The game's deterministic. Like there's no randomization mechanism, just flipping a coin or rolling a die or something like that. And there is perfect information in the game. So each player knows all the information about the state of the game and nothing is hidden. So we shall discuss in particular combinatorial games which are bound to end. And we also impose another condition in our discussion today. That is, these games that we shall discuss will be impartial, which means that the moves available depend only on the position of the game and not on which player's turn it is. So, so in our discussion, chess and checkers and all don't come under impartial games because the one person can only move his or her particular coins. For example, in chess, the person who's playing as white can only touch his white pieces, and then a similar thing holds for black. So yeah, so again, this slide summarizes what we mentioned in the previous slide. That is like we are, and the entire discussion will be based on finding what the winning and losing states are. So yeah, so the set P of all the positions can be partitioned into L, the set of losing, and W, the set of winning positions. Now here you can see that uh, like a person can either win or lose in such games, and then uh, like and no person can both win and lose at the same time. So the set of all positions is L union W, and L intersection W is the null set. So a player finding himself in position L will lose provided his opponent plays correctly. So also one thing that we shall assume in our discussion is that both players would make the best possible move in their position when it is their turn. So a player finding himself in a position W can force a win whatever her opponent does. To win, a player must always move so as to force his opponent into a position belonging to L. So this is the strategy for winning, right? So and from each position L, every move must result in a position in the set of winning states. And again, as I said earlier, from every uh, position in the winning state, a move to a position in a losing state must be possible, right? So, and also the set of losing states must contain one final position from which there's no move out, and this shows when the game ends, right? So, and as I mentioned earlier, we would like to find the set of winning and losing positions. So here's a Slido poll. You can try to solve. I mean, try to tell me what you think about you can try to answer the question in the poll by scanning the QR or yeah, by scanning the QR. So have you guys received the poll? Okay, nice. Yeah, so I have got a few responses here, and yeah, some people have marked 75% of people have marked 21, and yeah, and I believe the correct answers will be 21 and 25. So and I'll explain like why that is the right answer, and like for a more general problem. So yeah, here's the problem. There are initially n candies on the table, and this is like a similar thing. A player may eat any number of candies that are less than equal to k in one turn. The set of legal moves is eating 1, 2, 3, and so on till k number of candies. And a player must eat at least one candy in a turn. The winner is the one to eat the last candy and find the losing positions. Right? So we shall first try to make a conjecture on what could be the set of losing positions. And like we start with the following way, right? So all positions containing 1 to k candies are winning because the person who is starting the game can eat all the candies and win the game. And however, the position where there are k plus 1 candies on the table is a losing position because the starting player must eat some non-zero number of candies that is not k plus 1 and make the number of candies available less than or equal to k, right? So the second person may then eat all the candies that are available on the table, and then he can win easily. Now, what happens when there are k plus 1 plus x candies on the table where x is in between 1 and k, right? Here, the first person will definitely win if he plays optimally, as he can eat these x candies and leave out k plus 1 candies on the table. And this, since k plus 1 candies being on the table shows a losing position, this guy, the first guy, will definitely win. Right. Also, by using a similar argument, you can find that 2 into k plus 1 is a losing position. Right. So we now conjecture that like when there are multiples of k plus 1 number of candies available on the table, the person who's starting the game will lose because whatever the first player makes, the second player can force him to get another multiple of k plus 1, and this process continues till there are no candies left. So you can think of it as some kind of proof by induction or something. You can try to prove it using induction. And yeah, so the answer to the problem is the set of all multiples of k plus 1 candies being on the table. And in the problem I gave in the poll, k was 3. So all multiples of 4 are losing positions. So, and the winning positions will be anything that is not multiples of 4, right? So that's 21 and 25. Yeah. So this is like one class of problems that you can try to come up with solutions for. So yeah, I've also attached a couple of, I mean, two more similar questions in which you're supposed to conjecture which could be the winning and losing positions, and then prove your claim by induction. But like I would also want to discuss the situation where there are 100 or many different allowed moves, and all of them are at random, and you are asked to find out the winning and losing positions. So it is going to be very hard to do this by hand, and it's quite difficult to even come up with a conjecture and then to prove it. So we try to use some algorithm to solve this problem, this kind of problems. So now I have like selected a problem from like one of a very the most famous problem sets, that is the CSES problem set. And yeah, like I think everybody should do this problem set at least at some point in their competitive programming journey. So the question reads as follows. Consider a game where two players remove sticks from a heap. The players move alternately, and the player who removes the last stick wins the game. And he's given the set of allowed moves. So the person can remove any number of sticks that is given in the set P, right? So this is very similar to this. This is just a generalized version of the problem we had done earlier. And the input to your like the input you get has two integers, that is n and k, the number of sticks available on the table or the heap, and the number of moves. So the next line has k integers, which are the allowed moves, and all of them are distinct, and one of them is definitely one. And you are asked to print a string of n characters where w denotes a winning position and l denotes a losing position. So so I shall try to, okay, maybe you can try to think about this problem for a minute, and then I'll explain what my approach to the problem was. Yeah, so I'll try to explain what my approach was. So we shall maintain an array of n+1 elements in which we store one if that particular number of elements. So let's just say for the ith index, that will denote the winning, whether the state where there are I elements in I sticks on the table is winning or losing. So we store 1 if that particular position is winning and 0 if it is losing. So we shall initialize the entire array with zeros. Now, again, the next few lines explain what I just told. And we also maintain the array P, which contains the different legal removals, right? So we follow the following algorithm. We iterate from 0 to n-1. And then when we are at position I of the array, that is, we have I sticks in our pile. If A of I is 1, we just continue. And I'll explain why we are just continuing like in a few minutes. And then if A of I is 0, then we iterate over the set of allowed moves, that is the array P. And for each x in P, we mark A of I plus x as 1. Now, why do we do this? So like the reason is when we have I plus x sticks, right, in the position where there are I plus x sticks, and x is in the set P, in the array P, the person whose turn it currently is can remove x sticks, and this is an allowed move as it is in P, and leave out I sticks for his opponent. And so the fact that A of I is 0 means that we have already processed that particular state and we have declared that it's a losing state, right? And then so this person as he can make a transition to a losing position, the person whose turn it is when there are I plus x sticks will win. So this I plus x sticks is a winning position. So that's why we mark A of I plus x as 1. Now I'll explain why we initialized each of the elements as zeros. Like this may seem a little bit silly, but I would like to make things as clear as possible. But so here's the reasoning. Now, if an element is not 1, by the time we reach it in our iteration, it means that there does not exist any j that is less than I, such that j plus x equals I for some x in the set of allowed moves P. And then A of j is 0 and A of j is 0, which means that none of the legal moves available to me. So from I cannot remove any. So whatever I remove, I will not transition to a losing position. So which by definition means that this position is losing. So like assigning all the I mean, initializing all the elements is 0. Like, make sure that I don't have to do any further operations to check this. Right. Also, let me explain why we did not modify any element when we reached a position I such that a of I is 1. Now, observe that for any x in P, I plus x, where so as mentioned before, I is such that a of I is 1. I plus x may be a winning or a losing position, which we don't know for sure right now. But like, we only know the fact that a of I is winning and x is an allowed move means only tells me that if I have I plus sticks and I remove x sticks, I will lose. So, but like, as all the elements in the array have been initialized to zeros, I don't have to change anything for now. I only have to make the change where a of I is losing and like x is an allowed move. So this approach that we have followed to solve this problem is quite famous in the field of computer science, and it's one of my most favorite topics, and it's called dynamic programming. So this is extremely useful in solving some game theory problems, right? And I've also attached a couple of resources to learn dynamic programming in a better way, and some game theory problems which are related to dynamic programming. You may go through them. I mean, after the session. So we are going to discuss a very famous game called the game of nim, and this is like the results that we get from this game generalize and help us find the winning and losing states for many other games that exist. So here's like this is very similar to what we have been discussing before, except that it generalizes some things. So given a number of piles in which each pile contains some number of stones or coins, in each turn, a player can choose only one pile and remove any number of stones, at least one from that pile. The player who cannot make a move is considered to lose the game. Yeah, that is the one who takes the last stone is the winner. Again, this game obeys all the rules that we discussed in the beginning. And just as a recap, yeah, both of them have access to the same kind of moves, and then both of them know what will happen. I mean, all the states of the game are clear to the players, and so this is thus an impartial combinatorial game, right? And if you haven't seen this game before, there are some unexpected surprises ahead. Yeah, so we shall try to find a strategy for this game intuitively. So it like the explanation that I shall be giving is just an intuitive explanation, and then it may not be completely rigorous, right? The first part of the explanation at least. Okay, fine. So we will assign a number to each state of the game, right? Which in some way determines whether that position is winning or not. We assume that there also exists a function which combines the two values for two states A and B to give the value for state A plus B. So what I mean by A plus B is like state A will have a set of piles, I mean set of piles of stones, and then so will state B. So I shall just place them side by side and consider the entire like the game with the entire set A plus B. Like this is probably trivial, but I just wanted to mention it. Now we shall denote this like this function by the operation nimsum, and I'll give a much more definitive explanation to what nimsum is little later. Now let A be the value for state A and B be the value for state B. For A plus B, by definition of the nimsum, A plus A nimsum B or B nimsum A is the value for state A plus B, right? As the order in which we place the piles don't matter. So we see that this operation is commutative. And then say we have a third game state C, which has the value like C, which has a nim value C, then A plus B plus C, like keeping all the three states side by side and constructing a new state, is A nimsum B nimsum C or A nimsum B nimsum C. as the order of piles does not matter. Like, and this should be pretty obvious. So the nim-sum operation is associative. Now we consider the state A plus A, right? And I would like to like give you some time to think about what the whether the state A plus A is winning or losing, and we will try to and I'll give you the solution in 2 minutes. Okay. So yeah, so first let's try to solve this problem in like a sequential manner. Let's just say that we have 2 piles of stones which have the same number of yeah, which have the same nim value, right? And then yeah, so that is they have equal number of stones. Now we see that the first person, the person who's starting the game, will lose as whatever how many ever number of stones the first person removes. The second person can copy the first person by doing the same operation on the other pile until there are no stones left in each pile. Right? So, and when there are when the number of stones in the 2 piles are not equal, one person the person who's starting the game can remove stones from the pile that has greater number of stones, so that both of them will have equal number of stones after his move. So essentially he'll make the second guy lose, right? So he's going to win. So what if there are multiple piles? So what if we have like let's just say 4 piles, one with let's just say X stone, I mean 2 with X stones and 2 with Y stones. So here, this is also a losing state, and like it's quite simple to think of it. So like this state, whatever I've described right now, one which has 2 piles with X stones each, and then 2 other piles with Y stones each, can be thought of as the state A plus A, where A refers to the state where there are X stones in one pile and Y stones in another pile. So this is also losing because again we can try to describe a similar kind of a mirroring strategy. If the person removes some number of stones, the first guy removes some number of stones from the pile containing X number of stones, the other guy can again copy whatever this guy has done on the other pile, and then ensure that ensure that the nim sum is 0, and ensure that he transitions to a losing state. And again, this is something like induction. So one other thing is clear: the nim sum of 2 different states, like A nim sum A, is 0. So let us try to find a function that we know in like computer science that mimics these properties, that has the same properties as this nim sum function. Yeah. So again, as I mentioned earlier, the presence of equal number of stones on 2 piles somehow cancel each other out. Right. So yeah. So I have summarized the properties here. A nim sum A is 0, A nim sum B is B nim sum A, and then A nim sum B nim sum C is A nim sum B whole nim sum C. Now let us consider the XOR function, right? So you know that if you have some number, let's just say 5 XOR 5 is 0, and then also if you have 2 numbers X and Y, X XOR Y is Y XOR X, and then you also know that it is associative. So we now conjecture that this nim sum function could be the XOR function itself. Now we shall try to prove that the nim sum function is indeed XOR, and I shall start calling this XOR because I find it like easier to say. Right. So the claim is the following: given a game of NIM whose current game state consists of n piles with P1, P2, P3, and so on to Pn. Yeah. Then the current game state is a winning state if the NIM sum P1, NIM sum P2, NIM sum P3, and so on till NIM sum Pn is non-zero, and a losing state if it is equal to 0, where NIM sum is the bitwise XOR operation. Yeah, XOR. So we shall attempt a proof by something that is like strong induction. It's not exactly strong induction, but it's something like strong induction. So for the state where there are no stones, the NIM sum is 0 and it is a losing state, right? And this is quite obvious. Like, yeah, that is the definition of the game literally. So, and when we are having some piles and stones, we assume that the theorem is proven from all states reachable from the current state, right? So I mean, so we have proved the theorem for all states that are, yeah, that like to which upon adding some number of piles and stones, we get this state, right? We get two cases now, okay? So the NIM sum S of the current state, whatever I have right now, is 0. Now, then here, like the first player removes some number of stones. Let's just say some X number of stones from a pile, say Pi. Then the new NIM sum becomes P1 XOR P2, XOR P3, and so on till Pn, which was the initial NIM sum, XOR Pi, XOR Pi minus X. So because the inverse of XOR operation is itself. So, and I hope you know this, like that the inverse of the XOR operation is itself. And if you do not, please type it in the chat box so that, like, yeah. So do you all know this operation? I mean, this fact? Hello? Yeah, if not, I would like suggest you to like yeah. So try out a few examples right now and try to understand why like this could be the XOR operation could be the inverse of itself. Right. I'll give you a minute or two. Actually, like maybe writing a truth table will help you understand better, or something like that. Something like a truth table, which will tell you if a bit is switched on or off. And I would suggest you to do it right now, because like doing it yourself is better than me telling you the thing. I think that will help you understand better. Okay, I hope you guys have done it. Yeah, I don't see any response in the chat box. Okay, fine. I'm going to continue anyway. I just assume that you guys know it. Right. So by the inductive hypothesis, that is what we started assuming, right? We said that for the theorem has been proven for all states reachable from the state, right? Yeah, exactly. So now the first term that was the NIM sum earlier was 0 before this particular person's move, right? So the current NIM sum is just Pi XOR Pi minus X. This cannot be 0 as X is non-zero, right? So like if I wanted pi XOR pi minus x to be 0, I should be having pi minus x to be equal to pi, right? Otherwise it cannot be 0. So since x is non-zero, pi minus this particular the nim sum right now cannot be 0. So the state has the reach state has non-zero nim sum and thus is a winning state, right? Which means that the current state is losing one. So whatever move this guy makes, he is bound to lose, right? Yeah. So what happens when the nim sum is non-zero? So if we pick the pile, if the person whose turn it currently is picks the pile with pi stones and removes x stones from there, the new nim sum will be pi p1 x. That is the current nim sum XOR pi XOR pi minus x. Right. That is the same thing as what we had earlier, but we shall try to establish that there always exists. I mean, there always exist such a pi and x such that the current nim sum becomes 0. So whatever be the situation, as long as the nim sum like before this particular guy's move was non-zero, right? So let us say n is the current dim sum and this is non-zero, like by like that's what we're discussing right now. Yeah, so if I want to make the new nim sum 0, n XOR pi XOR pi minus x must be 0, right? Like since that is 0, pi XOR pi minus x must be n. So this is the only way in which I can make n XOR pi XOR pi minus x to be 0. Now let us construct this thing. Right? Now let the largest bit of n be the kth bit. Now we pick a pile pi such that the kth bit is 1. Okay, and this should always exist because you cannot have the kth bit in the XOR of everything turned on with none of the things having its kth bit turned on. Right. So I hope you get what I'm trying to say. And we now remove some number of stones such that the remaining stones pi minus x has the following properties. Right. All the bits that are more significant than the kth bit are same as those in pi. So what I'm trying to say is, so kth bit is the largest bit in the current nim sum, that is n, right? And all the bits that are more significant, meaning all the bits that are to the left of the kth bit in the bitwise representation of n, will be the same as those in pi minus x, should be the same as those in pi, right? So that these bits cancel each other off, and then we would only have to deal with bits from the kth bit to the 0th bit. Now the bits that are less significant than the kth bit are such that pi XOR pi minus x's corresponding bits are same as those in n, because we want like pi XOR pi minus x to be equal to n, right? So yeah, and the kth bit should be 0, like because pi had the kth bit turned on, and then we just want and since we want the XOR to be n, we don't want pi minus x to have the kth bit on as well. So the kth bit of pi minus x should be 0. Yeah. So let me give you some time to think of like why such an x will exist. Yeah. So what we do is we write down. I hope you've got this, but anyway, I'll try to explain in my like what I have understood here, and like write down the bitwise representation of this pi, right? The pi that you've chosen. Now the k, you know that the kth bit will be 1, right? And then what we shall do is we shall like So all the bits that are before the kth bit shall not be removed from this PI, right? So we should wait. So we construct PI minus X such that this happens. Now, okay. So I've told you that all the bits to the left of the kth bit are not going to be removed, right? They're going to stay as it is in PI minus X as well. And we are going to remove the kth bit. And then now, like, since kth bit is on in PI, the like and you know that 2 power k is greater than 2 power k minus 1 plus 2 power k minus 2 and so on up till 1, right? Like by basic GP summation. So whatever be the bits that are on in PI minus X after the kth bit, that is the less significant bits. Like even if all of them are on, I would still have PI minus X to be less than PI. Right? So like I can say that X will definitely be non-negative in this case. Right? Okay, fine. So yeah, so such an X always exists. So whenever the nim sum is non-zero, I can always make a transition to a state where the nim sum is zero. And which means, and like by this like so-called strong induction kind of proof, we have been able to establish that whenever the XOR of all the states, XOR of all the like the number of stones in each pile is zero, that the person who's starting the game will lose. And then if the XOR of the number of stones in each pile is non-zero, the person who's starting the game will win. Right? And I hope this was clear and interesting. Right? So yeah, so this is the winning strategy for the NIM game, and this has a lot of applications. Now, however, like although like since we have some time left, do you guys have some doubts in what was discussed? Like, if not, just put a thumbs up. Yeah, like you may type your question in the chat box though, like if you have something. I'm not sure if other participants have been given unmute access. Yeah, I take that there are no more doubts. Yeah, okay, fine. So now I also would like to give you an interesting problem to think about, right? So here, let's just say that in the same NIM game that we have discussed for so long, that we've been discussing for so long, the person, like each player cannot remove any number of stones. He can remove only stones that are like, I mean, he can only remove 1 or 2 or 3 stones from each from the pile he's selecting. Right. So, like, I hope I'm clear. Like the person whose turn it is can select a particular pile and remove either 1 stone or 2 stones or 3 stones. Yeah, like on his turn. Now you would like to again find out who will win the game. I mean, how do you find out the set of winning states and the losing states? I mean, I would leave you to think about it, I guess. So I mean, it's surprisingly simple. It's pretty much the same thing, but with just a small twist. That's all. Yeah, I guess if you don't have any doubts, this is where I should end my session. I've also attached some like some more different problems and resources where you can read about more games, and like there are some generalizations of the NIM game which I yeah, have not been able to cover because it would take just as much time as I took for like covering up like the NIM game and stuff like that. Yeah, so otherwise this is where I'm going to stop. Thank you all.
Am I audible? Hello, clear? Yeah. Yeah, hello all. I'm Varun Kaushik. Today we'll be discussing the essentials of number theory and GCDs, all the subparts like geometrical part, not geometrical part, but number theory part required for CP. So let's start. So in this session, what all are we going to discuss? First, we'll give some introduction of what we are going to learn and how this is related to CP. Next, we'll go through the Euclid's algorithm. Next, see of arithmostats, then segmented sieve of arithmostats and Euler's coefficient function. Names may be some complex type, but they are quite easy, but they have a lot of extended application in computer program. So I'm Varun. So we will be dealing with all the necessary number theory and DC techniques required for CP in the future specifically. There are a lot of questions based on only number theory, which finally turn to be of number theory only when you deeply analyze the question. So these techniques will help a lot while doing CP. So let's start. So first of all, we need to find some algorithm to find GCD of two numbers A and B, let's say, and we should find the algorithm such a way that it doesn't take too many operations. So that's one of Euclid's. In that, Euclid's algorithm will give our help. It's one of the fastest algorithm. It's the fastest algorithm, right, as of now. So what's this algorithm all about? Let's say two numbers A and B. Let's read the definition here first. Originally, the Euclid algorithm was formulated as follows. Subtract the smaller number from the larger one until one of the numbers is zero. Indeed, if G divides A and B, it also divides A minus B. Now let's understand this. Let's say A and B are two numbers. If a number G divides A and B, then obviously the number G divides A minus B. So what it finally comes down is if A and B have the common divisor as G, then B and A minus B also have the common divisor as G only. So this is the fundamental algorithm for Euclid's algorithm. So, but we cannot keep on doing subtracting B every time like that. So it will take so many operations. Now, smartly, what Euclid's algorithm suggests is like this. Implementation, it's like this. We'll do, it's a recursive function. First, we'll take inputs of int A and int B. If it's 0, then what? That number is dividing that one. That means A is the GCD of that number. Else, we'll do B, comma A percent B. Why A percent B? We'll keep on subtracting B until A is less than B. That's what we're doing here. We cannot keep on subtracting B every time. So what we'll do is we directly take remainder of B with respect to A such that it comes down a number which comes down less than B, and it's also somewhere related to A. So like that, this will take only log of an operations, and this is the fastest algorithm. So in this way, in this way we'll find GCD in general for any, like, there is an SQL also underscore GCD A comma B, which directly gives the GCD which follows the Euclid's algorithm. But this is how actually how it comes. So for LCM also, we use this technique. We know that LCM of two numbers into GCD of two numbers equal to product to the two numbers. So LCM equal to A star B by GCD of A comma B, which indirectly is the log of n, O of log of n, because A star B is O of 1, remaining is log n, so log n is bigger. So LCM also we can find in log n. Like that, we can use GCD to find LCM also. So next we'll be discussing C of aristostats. This is an algorithm to find all the prime numbers in a segment, 1 to n. So uh, we have an n root n approach, we have an n square approach, we have a lot of approaches, but we require a much optimistic approach than those, because all in CP time, your time complexity is one of the most important topics, because before you're submitting questions, few questions will be very easy to brute force it, but actually they are very tough when you go into deep. When you know the actual algorithms, you'll find them very tough. So C of aristostats is one of them. This is one optimization technique to find prime number. So we'll see how this works with a new figure so that we get a clarity how should we write implementation. There is taken we want we want all the primes from 1 to 16. So we anyway know 1 is not a prime number. So we remove it from the vector, or whatever data structure you use. We remove it from them. Next, we'll take the first prime number which is not marked. That's the way how it works. First we'll take 2, then we'll mark all the multiples of 2, like that: 2, 4, 6, 8, 10, 12, 14, 16. Like that, all the multiples of 2 will be marked till n. N is 16 here. Then we'll see the next number which is not marked. That is 3. Then we'll keep on marking the multiples of 3. Those are 6, 9, 12, 15. 6, 9, 12, 15 are not any more primes because they are factors of 3. Now, after 2 and 3, we see that 4 is already marked. So what we'll do is we'll jump on to 5. We'll mark all the multiples of 5, that are 5, 10, 15, and so on. Like that, we'll keep on continuing all of them, and you get the primes in the list of 2 to 16. This works on the basic principle that if a number 16 is there, maximum we can using root and approach, we can find all the divisors for 16. Same approach is using here. Like that only we are finding how to do this. 2, 3, 5, like that. We keep on doing like that so that we get number of primes between 2 to 16. This is how it works. Now let's see the implementation how to do. This is the implementation of C of aristostats. We will take the number n till where we want the primes. That will be a Boolean array, or true or false. Actually, there is one fact that Boolean arrays are very fast. If you store it as 1 or 0, it will take more time than Boolean array. So, in general, if we want to do these questions like this, we'll use a Boolean array. So, first we'll take is prime, is 0, and 1 is false, because these two are not true, because 0 is not a prime, 1 is not a prime. So, we mark them as false. For int, this is the loop running from 2 to n, I plus plus. We don't know what all can be there. Now, actual code is like this. Still, if statement and the for loop inside is the actual code. See, now, first we will take 2. We know that 2 is not marked as false, so it will enter the loop. And if 2 star 2 is less than or equal to n, that means I told you, we can find the all the devices of n less than O of root n. The same logic here. I star I less than or equal to n. Otherwise, it won't be a case. It will be possible. So we'll start from I star I only. Then j will run till it's less than or equal to n. And as you know, we will keep on adding its multiples j plus equal to I, like 2, 4, 6, 8, 10, like that. All those multiples will keep on marking as false. That means next time when 3 is coming, 3 won't be as marked as false. So it will enter the loop again, but 4 will be marked as false from the 2 1. When we take 2, j equal to 2 star 2, then j becomes 4. Then each prime of 4 becomes false. So that marks as false. Next time when we enter this if loop, we see that it's false. That's why it does not enter that it does not enter the if loop. Then it will go to the next I and continuous iteration. In that way, we'll get all the prime numbers in this. Then we'll print what all we want. If it's true, we'll print out C out I like that, and we get all the prime numbers. This is the fastest way. It's of analog and approach. So this is the one of the fastest technique to find C of stacks. So there is one extended thing, extended C of stack, that is C segmented C of stacks. Let's say you want to find all prime numbers in a range. Now in the previous one we discussed the numbers for 1 to n. Now we will discuss the numbers in range L to R. Like we don't know the start. We are not taking the starting number as 1 to n. We'll take that starting number as some random number L, and the final number let it be R. So small size, it won't be a much problem. But if R is a large problem and the interval is very big, then it may not pass the cases when you're taking. If you find all the devices till R, then all the devices till L, it may not pass. I already told you CP is one of the Hello. 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 Am I audible? Okay. Shall I start? Okay. Re- yeah, am I audible? Hello.
Yeah, you're audible.
Yeah. Now let's see the implementation of it. Let's say vector will take one vector, we'll return one vector finally so that we use it for printing. This is a segmented C function. We'll input the L and R, upper limit and upper left limit, lower limit and right limit. Both are long. We cannot, as if it's some funny 12 or something, it cannot store in this one. So we'll take as input as long. Then limit we'll take a limit as a number square root of R. This we this for finding limit, why are we doing like this is we are using the fact that all the prime numbers less than root R will divide some all the other numbers. That's the fact we are using here. So which are using the sieve of using the sieve of stats, we'll find all the prime numbers till root R. Then that's the only thing we are using here fundamentally. Then remaining is normal logic only. Let's see how. Let's first of all we'll mark one array vector char mark of limit plus one false. That means what? Till root R plus one we take one character array and vector long primes uh, till two to root same as sieve of stats. We'll mark all the prime numbers here. Then actual extension of sieve of stats segmented C starts here. Here, what we'll do is we'll take one character vector character again, is prime, like same way as your first style, r minus l plus one, comma true. Then this is one auto function type, long I is to prime. That means it will take till all the values of primes. Here, what we'll do is j equal to max of I star I, comma l plus I minus one by I star I. Can anyone say me why this second term has come? L plus I minus one by I star I. Can anyone can we see in chart? Hello. what we what we are basically doing is we are finding the next upcoming to just after L. So if I star I is greater, then we'll take that. If this is greater, we'll take that. It's just like we are taking if I star I is less than this, then we no need to consider that it will anyway come there. So till j less than or equal to R, we'll keep on adding I. That's the multiple prime multiples like C only again. and we'll mark J E prime J plus. So, uh, Anna, I'm audible now. I think it will be fine from now on. Hello. Yeah, okay. I'll start from again from segmented C. I think some of you will not hear. Okay. Now, segmented C of resistors. Sometimes we need to find all prime numbers in a range like L to R of small size, approximately 1e7. Actually, it's not a small size, but in compared to CP programs, we say it's small size, and R can be very large. For this kind of questions, we cannot use Sievert resistor. So, which we will use now as extended thing, which is called segmented Sievert resistor. Now, to solve such a problem, we can use the idea of segmented sieve. We pre-generate all the prime numbers up to square root of R and use this prime to mark all composite numbers to segment L to R. See, now is the same idea as Sievert resistor. Till root R, we'll find all the prime number, which can be, which will divide. If it divides any number there, it will divide surely any number between L to R. So if we find all the prime numbers up to square root of R, then our 50% job is done. And the remaining 50% is done when we mark all the composite numbers between L to R and we mark them as false, which indicates they are not primes. So now we'll see how we will implement it using our C++ code or C anyway. So, let's say first we'll take, as I told you, we'll take on vector char everything. It can be taken as Boolean array also, we don't mind. But vector, we'll take on vector char long L. We'll take long limit is equal to square root of R. As I told you, we'll generate all primes up to square root of R. Then one vector will mark, vector named mark limit plus one to all of them will mark false. This is till from here to here, whole part is of C of aristocrat, which marks all the prime numbers between uh, 1 to square root of R. So I don't think I should explain all of this again. Now we'll see the extension for this. How does it work? Now let's say we'll take one vector e prime minus L plus one, which will be the size of the interval. We already generated all the primes and stored them in the primes thing, primes vector. So this is an auto function which will run all the loops till all the primes are covered. In the second for loop, what we'll do is same as C of S stat, we'll keep on marking all the multiples and we'll take maximum of I star I comma L plus I minus 1 by I star I. Now, someone has to say why L plus I minus 1 by I star I has come. If only I should have taken I star I. Why does this L plus I minus 1 term come again? Can anyone say to me in chat? Anyone? Okay, I'll continue. It, it indirectly means that we are taking the closest I star I multiple, which is close to L, and we'll take maximum of I star I and this, which indirectly says that if this is greater, we no need to consider from I star I. Directly, we can take from this. If this is greater, I star I is greater, then we need to no need to consider from L plus I minus 1 by I star I. We can take I star I directly. Same logic as C of S stat. Here we are not taking as I. We are starting from I star I. That's there is one number theory proof why we are starting from I star I. Uh, which I don't want to discuss. It's a big time. It will take some time. So that's the same logic as here. Same logic we are keeping. We are applying here, and we'll find like this. Same again. East prime j y minus l. We are only taking an interval of r minus l plus one size. So we want as vector cannot store all the values from 1 to r. So we will take a interval East prime j minus l equal to false. East prime j minus l, which is related to L, such that interval don't last much longer, and we can store all the values in vector character. So same as this logic, we'll all the composite numbers will keep on marking false. Then if L equal to 1, then we'll mark East prime 0 is equal to false because we know 0 is not a false number anyway. And we'll return the East prime vector, character vector. So this is how segmented C of X stat works. So if everyone understood, give a thumbs up there. Attendance, I'll keep it at last. The QR is at last. After this session, you'll get your attendance. Shall I move to the next one? Okay. Now we'll start with Euler's Gaussian function, also known as phi function or phi of n. We denote as phi of n. Counts the number of integers between 1 and n inclusive. This is one of the most important functions in number theory, but some important questions will be there, some good questions will be there, which turn out to be from Euler's Gaussian. But we should be very careful while solving this question because your presence of mind should be very high because even one interval, if you do wrong, you keep n equal to I equal to 1 or something, then whole thing will go on segmented fault. That means it will keep on running. So you should be damn careful while you write this program of this code. So what this illustration basically does is it counts the number of integers between 1 to n, which are co-prime to n, including 1 and n. 1 is anyway co-prime to n because the GCD will be 1 only. So n cannot be co-prime to n because GCD will be n now. So indirectly, it's all the co-primes from 1 to n minus 1, which are co-prime to n. Indirectly, it comes down to that. Two numbers are co-prime if their GCD greatest common divisor is equal to 1. If someone don't know, I have added this point. 1 is considered to be co-prime to any number because GCD will be 1. So with any number, GCD will come down to be 1. So let's see what we can do with this. These are some of the standard values for n equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, like that. All these are phi of n values, but you cannot just keep on counting till 1 to n. That will take a lot of time. So there are some optimized algorithms for this, and there is one interesting result of phi of n directly is like a formula, mathematical formula. So we'll see that. Let's say first we to prove that formula we'll use some results now. The properties of Euler's Gaussian function are sufficient to calculate it for any number. If that's what I was saying, if we know all the properties, important properties, then we can find Euler's Gaussian like an basic math formula. We don't need to calculate to check with every number. So if let's say P is prime number, then GCD of P comma Q is 1, obviously, because it's a prime number. Let's say if only if Q is less than P. If it's greater than P, let's say 6 and 3, P is 3, let's say, but Q is 6, it cannot be 1, right? Because it's not greater than it. It's greater than it. If it's less than, it cannot be P. It should be only less 1 only. That's what for all 1 less than or equal to Q less than P indicates. So we have phi of P is P minus 1. Makes sense? Till 1 to P minus 1, all of them will be co-prime to P. That means phi of P will be P minus 1. Now, if P is a prime number and K greater than or equal to 1. Let's say K is a number, integer, which is greater than or equal to 1. Then there are exactly P power K by P numbers which divide 1 and P power K. And that are divisible by P. That means what? Phi of P power K will be P power K minus P power K minus 1, obviously. All the numbers that divide, which P divides minus total number of numbers in P power K. That means phi of P power K will be P power K minus P power K minus 1. This is one of the fundamental results. We can mark this. Then another result which comes from Chinese remainder theorem, but Chinese remainder theorem is little tough to explain and it's a difficult thing. We cannot discuss in 45 minutes, so I have not added. But remember this, if you want to search it up, Chinese remainder theorem, if you want proof of this, if A and B are relatively prime numbers, then phi of A comma B equal to phi of A into phi of B. This if you want to prove mathematically, you should use Chinese remainder theorem, but common sensely we can say this is true. Okay, these two results will make whole base of phi of n. Let's see how. Let's say phi of n equal to phi, let's say n is equal to, we write as factorization, p1 into a1, p2 into p2 power a1, p1 power a1 into p2 power a2 into so on until pk power ak, which is basic factorization you all have studied at 10th or 9th. So what will be phi of p1 comma a1? We know p is prime. A1 will be some value of k. K is greater than or equal to, I have clearly mentioned. If it's 0, then it's p is not a factor of n. So that means a1 is also greater than or equal to 1, which indirectly refers us to k in the previous result. That means we can use the property here, p1 to the power of a1 minus p1 to the power of a1 minus 1, and we break down like this. Then take p1 to the power of a1 common in everywhere. We know that n equal to p1 power a1 into p2 power a2 so on until pk power ak. That all of the terms which we took common will take it to front, and which product becomes n into 1 minus 1 by p1 into 1 minus 1 by p2 and so on until 1 minus 1 by pk. This is the mathematical formula which I was talking about for phi of n. Now this we got mathematically, but how will we tell the computer to find it? If a number n is given, we don't know the prime factors, right? So how will we find out the values? First, we have to. There are two standard approaches. We'll discuss all of them. Let's say phi of p1 comma final formula is like this: n into 1 minus 1 by p1 like this. So if a number n is given, how will we calculate phi of n? That we'll see through the implementation of C or C++ code. Let's say phi of n is an integer. Obviously, we know that's why the function returns an integer. Int phi int n, the number n which I will give you, int result equal to n. This for loop, what it does is factorizes the number. This is the factorization number. Now we have seen that n into 1 minus 1 by p1 into 1 minus 1 by p2, so on until thing. This for loop does that, n into 1 minus 1 by p1 and all. This is the method of factorization. There is normal logic. We can use segmented stage. We can think how. That's also a good method. This is of square root of n. That will be of different time complexity. This we'll find the factors, like we'll find the prime numbers when we divide by n% I equal to 0. When we divide I, then basically drops down to the what we want the result, which will subtract result minus equal to result by. Then you'll come out if the number n is prime number. Then what it happens is, it in any case n% I won't be 0. So nothing more change happens. So we want to subtract 1 there. So indirectly I am doing that only. But if n greater than 1, then what we will do is result minus equal to result by n. Now what does it mean? If the n doesn't enter here, then n will be here. If it will pass if clause, then n minus equal to result by n. That means n minus 1 will be the result value. That is if n is prime number. That's what I'm saying. Phi of k, if k is a prime number, that becomes k minus 1. So that's what this if condition gives us. Then we'll return the value of result. Is everyone clear as of now? Okay. Now we'll see one basic example of how this is done. How we'll use the number theory. It's a basic example, but in problem set, I'll give you good questions. In that, you can solve. This is the example just to give the flavor of GCD and number theory. So let's see the question right now. Given an integer array, return the sum of divisors of the integers in that array that have exactly 4 divisors. Okay. You are given an integer array. That means you have some numbers a1, a2, a3. You should return the sum of divisors of the integer in that array that have exactly 4 divisors. If a number has 4 divisors, then you should return the sum of divisors of the integer. If there is no certain integer, you should return 0, which is obviously true, but uh, just to keep in track, I am adding the statement. So, how will you tackle this question? Anyone? It will be an idea of factorization, which I will talk you. Anyone? Keep it in chat. Okay, let's go to the hint. It's similar to factorization or finding the factors. This is the key thing which I have discussed here. The factorization thing, n% I equal to 0, it will be similar to that. Now we'll see the implementation, what I was asking, what the code actually says. This is the code for it. Let's say we'll take temporary to LL is long. I used has different to do that. LLC equal to 0, LL sum equal to 0. I have told you till, let's say you have to do it for every element. That's why I took A of I. One loop will learn to till I equal to 1, I equal to 0 to I less than n, that n will be the size of the array. Then you will be finding factors of A of I. If A of I percent j equal to 0, then what you're doing? If let's say j is some, if A of I is 36, then j is 6. Then we are not getting two different factors. We are getting only one different factor. We're getting. So what we are doing is c plus 1 equal to 1 and sum plus equal to j. No need to add 2j because only one factor we are finding there. That is 6. If both are different, if j star j not equal to j star j not equal to a of I, then it's not a of I is not a perfect square with square root with root j. Then we'll add cs2 sum as j and a of I by j. What is that? A of I by j is first number. Let's say take 36. Suppose we are taking 1 into 36, 2 into 18, 3 into 12, 4 into 9. Same logic here. If those two are different, then there are different devices there. So C will store all the number of different devices for A of I. Then when we'll come to the new element, then C becomes 0 again, sum becomes 0 again. If C equal to 0, there will be one. Let's say we'll continue to this. C plus equal to 2, sum plus equal to j, sum plus equal to A of I by j. This gives the sum of j comma A of I comma j, which are the factors of this A of I. So then if j star j equal to I, c plus equal to 1, sum plus equal to j. If the question says if the number of divisors equal to 4, then we want all the sum of the divisors. Here what we are storing in the sum is we are storing the number of divisors of sum of the divisors of each A of I which we want. And we are in C we are storing the number of divisors of A of I. If the number of divisors of A of I equal to 4, then we'll add sum to answer. Otherwise, we no need to answer. At last, we'll print, after traversing through the whole array, we'll print the answer, which will give us the final answer. I hope everyone has understood. Now, I think this is the end of the session. Yeah, this is the attendance form we are all are waiting for. Take a QR of it. Take screen, whatever. Scan it. Everyone has scanned. Yeah, I think many of you have scanned. Now take a few minutes to fill the feedback form. Okay, thank you. I think most of you have enjoyed. I hope so. Shall we undo this part? Hello. Okay. Thank you for